graphs yourself. So we need to investigate some of the things involved with graphing what they call exponential functions. Let's do this here. Just as a quick note, you're used to seeing functions in this class. It looks something like this. X raised to the third power. That's x cubed. And you can actually, believe it or not, if I prod you a little bit, tell me something about this, like what it looks like on a piece of graph paper, roughly, like an S sort of shape. You also tell me what the domain is, all real numbers, maybe even some of the places where it's increasing, decreasing. We've been through a lot of these types of functions. You know a little bit about it. So now what we're going to do is we're going to create a new function that's going to look like this. This time we're going to take a number and we're going to raise it to a variable exponent. You can see now the x is not in your standard line of working for math. It's now where? Up in the exponent, so that would probably motivate the name exponential function, okay? Because obviously the function now is in the exponent. A lot of things change when this happens. Now, first and foremost, we're going to define these things as really going to be not just 3 to the x, but any number a to the x is going to be an exponential function. So this is an exponential function. We have to talk about these choices for a. Remember, x can vary from minus infinity to infinity. X is a variable. It can take on all kinds of values, including fractional values, right? X is a real number. We've got integers, we've got fractions, we've got even irrational numbers are real numbers. So when we think about that, if I was to ask you to graph something like 3 to the x, one way you might do that would be to create a simple table of values over here. We would have x and then we'd have f of x. And let's just look at what's happening right around the origin. Minus there, sorry. Just to see if we can see some of the things that are going on here. Well, if f of x is equal to 3 to the x, what is 3 to the minus 2 equal to?
1/9.
Yes, it's 1 over 3 squared, which is 1 over 9. So this value becomes 1/9. How about 3 to the minus 1? Now 1 over 3 to the positive 1, which is simply 1 over 3. 1/3. How about 0? What is 3 to the 0 power? 1. What is anything raised to the 0 power? Anything raised to the 0 power is 1, provided that, let's look at this, a to the 0 equals 1, provided a does not equal what? Right, you cannot raise 0 to the 0 power. So therefore, when we're looking at our functions for exponential functions, the base had never better be what? 0. So that's why, if you look at this first box over here, we're going to restrict a to be strictly greater than 0. Which also, by the way, removes all the negative values for a. We'll talk about that in a minute. But when we get to this, you'll see why a can't be 0, because if it was 0, we would have no way to do this particular part of the function right here, because you cannot raise 0 to the 0 power. But in this case, we have a 3, so that would be a 1. Now, what is 3 to the first power? Simply 3. And what is 3 squared? 9. Now, if we start graphing some of these things here, we have our first value of 0, 1. And that's a nice place to start. And notice that, well, at x equals to 0, what's the value of all exponential functions? 1. And that's a good way to start when you consider we're going to be using units, so it's usually the first unit. And at positive 1, we have 1, 2, 3. And at positive 2, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. At negative 1, we have 1/3, it's roughly right there. At negative 2, we have 1/9, which is right there. And perhaps you can see this, I can draw it better, sort of behavior like this. And if you look at the way things are going when you take off from the positive values or from 0 and you head this way on the x-axis, this thing's getting big, right? And as you go out on the x, it's getting big in a big hurry. For example, put in 1, 2, 3, 4, 5. When you have 5, what is 3 to the 5th power? 243. I just remember that from last class, but you can check on a calculator. 3 to the 5th power is 243. So already at 5, I'm up here at 243. So you can see this thing is growing fast, and oftentimes people refer to things as growing exponentially, meaning growing quickly? Well, then you can see why. This is growing at an awfully fast rate. So what I'm after out here is somebody to tell me where I can invest some money that grows exponentially. Because I got retirement coming up, not too long. I need my money to get big fast. Anyway, that's just an idea to model this. Look what's happening on this side over here. As we come down in towards the negatives, this thing is getting closer and closer to zero because each time we put a negative exponent in, it just drops it down to the numerator, becomes denominator, becomes positive, and it's growing. As the numbers get big at the bottom of a fraction, what happens to the fraction? It gets smaller, like 127. Then we have 181st power, and then 101 over 243. Those numbers get smaller and smaller and smaller and smaller, so you get this behavior right here. Now the question is, will it ever punch through this zero and get into the negatives? No, it can't, because all the negative exponent will do is make it a positive denominator. We're still dealing with positive numbers. Awfully small positive numbers, but positive still. So we call this an asymptote. It comes out here, it rides along zero for the rest of the way. Okay. So I said before here that A can't be zero, because if A was zero, at one point we'd have to raise 0 to the 0 power, and that would be bad. Not to mention, at all the other points, what's 0 to any other number besides 0? Well, for negatives, you'd have to put it down into the denominator. You'd be dividing by 0, and that would be horrible. And for all the positive values of x, 0 to the second, 0 to the third, 0 to the fourth is all what? So it just doesn't work at all, does it? So we're going to restrict the values for our base to be greater than 0. Why not negative values for the base, though? What's wrong with that? For example, let's just redefine this whole function over here. This time we're going to say f of x is equal to minus 2 raised to the x. This is an illegal operation. You'll see why in a minute, but what's really going wrong here? Well, put in minus 2 and you get, let's see, minus 2 raised to the minus 2 would be, well, minus 1 over 4, that works, minus 1, 4. Raise minus 2 to the minus first power, that's going to be negative 1/2. Oops, put that backwards. Put in 0, you get 1, that works. Put in 1, you get minus 2. Put in 2, you get, well, let's see, what's minus 2 times minus 2? Positive 4. Put in 5, you get negative 32. So I'm getting values here, that's okay. How about this? Will you put in x equals 1/2 for me? If you put in x equals 1/2, what do you get? You get minus 2 raised to the 1/2, which is the same thing as the square root of negative 2.
It's imaginary.
And this is a real graph. If this is an imaginary number, we've got major problems. As a matter of fact, at 1/4, at 1/6, or at 3/2, or anything that has a bottom number that's even, you're going to have the even root of a negative number. There'll be lots of big problems with this graph. So to avoid all of this, we just make sure that the value for a, the value of the exponential function, is bigger than 0. Can't be negative, it can't even be 0. It's bigger than 0. But then there's another one too. What happens when a is equal to 1? That'll be 1 raised to the x power. What's 1 raised to any power? So you'd have a straight line, 1, 1, 1, 1, 1, 1, and that's pretty trivial as well, right? So we don't want that happening. So we have two values here, 0 and 1, that it can't be, and of course all the negatives are out. And this sort of breaks the real line into 0 to 1 and 1 to infinity as far as the different choices for a. So if we start working with the choices for a bigger than 1, i.e. I use 3 over here, notice that we get this exponential growth thing happening. What do you suppose happens when I put values in between 0 and 1, which we also call what? Values between 0 and 1 we refer to them as fractions, right? 1/2, 1/3, 1/4, 3/4, that kind of thing. What do you suppose happens to the graph when I do that? Well, it actually becomes an exponential decay, and let me show you why in an example. This time we're going to use 1/2, okay? So, again, my x, y chart, minus 2, minus 1, 0, 1, 2. These are choices for me around the origin for x, so